Hello. So I explained what's the homoscedasticity and heteroscedasticity, and then I show you how you can implement the heteroscedasticity robust standard error. By the way, even if the model is homoscedastic, still heteroscedasticity robust standard error is fine. So if the homoscedasticity assumption is true, the default standard error formula and robust standard error formula are both okay. But when the assumption is wrong, then only the robust standard error formula survives. That's why the authors encourage you to use the robust formula, which makes sense. And as you see, the implementation is pretty simple, and interpretation is the same. There is no difference in the interpretation. So that's the bottom line. So simply put a comma robust at the end of your stata command. That I will take it as a default in this course. So throughout this course in this semester, I recommend you to use the robust formula. And the textbook has additional topics which I'm going to skip here, but I will mention two things. So skip, 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 skip. Not so good thing. Here, um, one potential problem is that so far everything about the OLS and the regression model was beautiful. I like it looked like perfect, but actually not. It cannot be perfect. So one big problem, potential problem that you may encounter in your analysis, in your work, is that the OLS is very sensitive to outliers. So even if we have the assumption that the outliers must be rare, but that is just an assumption, theoretical assumption. So in practice, you have to see if there is an outlier or not. So it is the assumption is purely theoretical. It does not do anything for you in the data. So you have to worry about if you have a strange result or like too good a result, then you need to worry about if there is any outliers. So like just a few number of outliers can change the results in a totally different way. So you have to be worried about potential outlier problems, and then I'm not so sure if I will have any chance to talk about this, but on alternative, when you see an outlier, or if you do not want to drop the outliers, then median analysis is a nice alternative. Instead of calculating the conditional expectation of y given x, you can calculate conditional median of y given x. So it's technically a little more complicated, and the estimator is called the least absolute deviations estimator. So this is similar to the idea that mean is more sensitive to outliers, but median is more robust, stable against outliers. So when you are worried about when your data have outliers, then think about median regression methods, which I'm not going to cover maybe in this course. But like if you know this, then later you can simply search for that, and implementation is not much different from regression. So that's one thing I wanted to say. And another thing here is, in case if you have taken another course teaching similar stuff, I believe you have learned, then you might have learned student t distribution. So student t distribution is basically the same result. It's the sampling distribution of the OLS estimator under a different set of assumptions. The main difference here is to have this student t distribution, you need to assume that the sample, the error term is homoscedastic, which is okay, acceptable up to this point. But you need even more assumption, additional assumption that the error term is normally distributed. This part is very strong assumption. Normal distribution is sometimes questionable. So if you believe that the error term is always normal, then using this approach does not cause any problem. But in general, it is a very strong assumption because uh, you don't know how the error term is distributed. And instead of adding the normal distribution assumption, we do not need the student t distribution does not require large sample size. So remember, we used the central limit theorem to have a normal approximation. So the sampling distribution is approximated to a normal distribution. The required assumption was large sample size, large n. But in this case, student t distribution can be an alternative if you have normal distribution assumption with small sample size. Then student t distribution could be better than the normal approximation. But in general, I think it's pretty much useless. So that's why the authors, the textbook, does not take this seriously. And we'll skip that. And so here is the difference. So why don't we need the t-statistic? Because as the sample size increases, so for sufficiently large sample size, the t distribution will be approximately another normal distribution. So t distribution will be approximately the standard normal distribution. Then why do we need a bridge? So directly approximate. So your sampling distribution is fitted to the student t distribution, which is approximately a normal distribution. But I would just drop the t distribution and directly approximate the sampling distribution to a normal distribution. That's my approach. And here you can see that. So as the degrees of freedom, you can think it as the sample size minus the number of parameters you are estimating. So when it is infinity, by the way, first let's think about the limit. So when you have infinite number of data, your critical value will be 1.96. Remember this number. 5% implies 1.96, and which is the true value in the limit. But if you have a sample size of 60, then it is only 2.00, which is pretty much the same as the limit. And think about this. If you have a sample size of 60, then you have this much approximation error. But in many cases, you have several hundred. The sample size is usually like several hundreds these days. So your approximation error will be much smaller than this. Then why do we need to think about the student t distribution? I think it is not that efficient. I think t distribution is not worth studying these days because, so remember the point, you need a large sample size. So usually the authors say more than 50, but it is really easy. Having more than 50 observations is like it's like observing quarterly data for 12 years or so, which is not that difficult these days. We have maybe data analysts from like for the recent 20 years or something like that, or from the World War II. And almost always it's not a big problem. So I do not teach student t distribution here. And so practical implication. So first, when the sample size is small, then you may need to think about the student t-distribution, but I believe you are not going to see this kind of cases. So small sample size causes many other problems, not only normal approximation. So it's a very uh, I want you to avoid using any statistics method using this small sample size. And second, be careful of making the homoscedasticity assumption. It's not necessary, and you don't need to make that assumption, which could mislead your results. Okay, that's it. So this is the end of chapter 5. Oh, in the next chapter, we are going to consider a generalization of the regression model to a multiple regressor case. So you have what happens if you have multiple variables, and can we analyze them at the same time? Yes, and we are going to study that later. And I'm going to post homework number 2, and maybe I will illustrate the data using the homework. So see you there. Bye.